Hi, this is Chris Nelson, Director of Sales Engineering for North America at Nexenta Systems, and wanted to do a quick webinar for you all. Should take about 30 to 45 minutes, depending on kind of the pace of how we go through this, covering just some basics that are pretty foundational to what Nexenta Store, our flagship software, is all about. It's built on ZFS. We'll get into some of the details here, but we want to cover some of the basics of ZFS, the hybrid storage pool, which is a key feature for us, the ZFS intent log, or ZIL, the two layers of caching, adaptive replacement cache, ARC, and the level 2 ARC as well. So we'll get into all of those in this seminar and our webinar, and let's go ahead and get started. So first and foremost, I think that one of the key pieces to understand about what Nexenta software, Nexenta Store is about is what makes it up. You know, what are the parts that come together to make Nexenta Store? And as you might guess from the title of this webinar, ZFS is core, central, and foundational to that. So ZFS, what is ZFS? ZFS is a file system originally developed by Sun Microsystems in kind of the middle 2000s. So this century, Sun invested over $100 million and many man hours into that project, and then subsequently incorporated that into Solaris 10, an update of Solaris 10, which they authored, and then later open sourced that. So Sun open sourced the majority of Solaris, including ZFS, and created a community called the Open Solaris community. And so now the open source community had access to this really leading edge file system and operating system. Subsequently, Oracle bought Sun, and Oracle has distanced themselves from Open Solaris, and most of the innovators from that Solaris and ZFS organization left Oracle. There are still some there, but many have left and have made efforts to continue that innovation in an open way and then productize it in various companies like Nexenta. And that's really, that effort is happening around a community now called Illumos. So the Illumos open source community is a fork or a continuation of the Open Solaris product or project, which was originally developed and started by Sun. So ZFS is the file system. We'll get into lots of details about that. Illumos is the kernel, the operating system that includes ZFS. And then on top of that, you know, that's common across all of the Illumos-based companies. On top of that, though, there are things that Nexenta has done separate from others that use Illumos as their foundation to make an enterprise-class storage software in our case. So there are some pieces of the Debian Linux community that we have integrated for packaging and for updating of software and such. There are a variety of things that we have done that are very specific to Nexenta that we've developed ourselves. The management interface, some additional work around replication and integration with cloud software, OpenStack, a new global namespace, NFS global namespace plugin that's available, HA cluster for high available configurations, and many more that are coming. Nexenta VSA for View is one that shows on the screen here. Some recent work we did co-developed with VMware to create a product that is designed for deploying and managing VMware View virtual desktop environments using Nexenta as the backend storage software without having to manage Nexenta as a separate entity. So that's the idea. ZFS is the core. That's what we're going to talk about today. But we've built on top of that to add a variety of additional features and things to make this core functionality really integrate into an enterprise class storage environment. Okay, so what features does Nexenta Store provide? And I can kind of highlight the ones that come from ZFS. So if we look at this, this is certainly not a complete list, but just give you a quick overview of really what the feature set is, or the majority of the feature set is for Nexenta Store in particular. Number one, it is a unified storage platform. So both NAS, Network Attached Storage, and SAM, Storage Area Network. So your NFS, your CIFS, FTP, HTTP, etc., that you expect in a NAS device. And then fiber channel, iSCSI, and future some block-based InfiniBand protocols as well on the SAN side. Really, it comes down to what hardware do you integrate, or what hardware do you put into the server that you've bought in order to run uh, NAS protocols over, for example, Ethernet, 10 gigabit NIC, for example, or a 1 gigabit NIC. More to come, certainly, as the industry moves forward. Or you could put a fiber channel HBA in, you could put an InfiniBand HCA in, all in the same server simultaneously. We could be serving multiple different protocols. So, unified storage platform, scalable to the limits of the hardware upon which it's run. Benchmarked on the Halem platforms at over 2.5 gigabytes a second of throughput through a single server. Um, uh, with the new Romley platforms, we expect those numbers to go up certainly. And current utilizes current technology. We'll get into solid state drives and such here fairly soon. Unlimited snapshot and cloning, that certainly comes out of the ZFS space. We'll talk a little bit about that in some of the future webinars in this series. Highly available configurations we can architect such that there is no single point of failure, no single card, no single cable, no single server, no single drive, no single chassis would be a single point of failure when architected that way. Some other things on here that stand out. Triple parity protection is one that only ZFS offers. So Nexenta being ZFS based offers triple parity. You can have triple parity protection where any 3 drives in a RAID set could fail. No other file system in the world today has that level of protection. RAID, you're used to dual parity or RAID 6 from other vendors and traditional file systems as kind of the high end right now. Integration with third-party applications and virtualization hypervisors and things certainly come into play here as well. Inline compression and deduplication, again, coming out of the ZFS foundation for us. Compression, we actually enable it by default, one of the levels of compression that we use, and then there are more that would require some more resource, certainly, but can give you even larger levels of compression. Deduplication as well is inline, not a post process like something like a NetApp, for example. And data integrity, we'll spend some time on that, so I'll skip that for the moment. And a couple other things: easy to use user interface, command line interface, graphical interface, and a programmable API for those who want to programmatically manage the system. That's just a sampling of features. There's certainly more. Follow up with Nexenta, contact nexenta.com, and you can contact people there if you'd like to know more about this. Download a free trial software, etc. So let's dive into ZFS. Right, this conversation we want to be about ZFS. So ZFS, we've already touched on kind of the history of it. What is it? It's a file system and, in a way, a volume manager in one. Right, so there is no more concept of managing RAID sets separately from what file system I want to put on it, or creating a LUN and then putting a file system on top of that. ZFS manages that all in one. We'll talk a little bit more on a subsequent slide here. Massively huge capacity. It's a 128-bit file system, which means if you're familiar with the addressable amount of bits, right? 128 bits essentially means that we can store more data than there exists in the world at a massive scale. So there is not going to be an expected point in the lifetime of anybody listening to this webinar where we need a larger addressable space for our file system. So we scale up into the zettabytes now, which is well beyond the terabytes and petabytes that we're talking about today. A pooled storage, and we'll come back to this hybrid storage pool here very shortly. So the key idea is automatic and intelligent use of a combination of RAM, solid-state drives in 2 ways, and hard disk drives. And we'll talk more about that. Always consistent on disk. We'll talk more to that as well. And the data integrity will be a follow-on slide. I've already mentioned a little bit of the snapshots and clones. We'll come back to that some as well. And one that we don't have really another slide on, so I'll mention here: simple and fast initialization, and it kind of in parallel to that, resilvering. When drives were only a few hundred megabytes or so, or several gigabytes certainly in more recent years, it didn't take too long to resilver or even initialize. If you went out in your file system said, I'm going to go write zeros on the entire drive before we start to use it, it didn't take terribly long, maybe hours, certainly not into the days and such that it's taking today. Right now, you can quickly go and buy a 4 terabyte drive for your enterprise, and there's word on the street that the Seagate and the other drive manufacturers are going to have 10 terabyte drives in the next 18 months or so. The amount of time it takes, right? The drive is still just as fast as it was back when it was 300 gigabytes. The amount of time it takes to
go write zeros across an entire 4 terabyte or 10 terabyte disk drive, um, and or to resilver, right? Most traditional file systems resilver an entire drive regardless of how much data is actually been written onto it. That is now stretching out into days, and then 10 terabyte drives. We may be out into weeks. So ZFS is different in that space. It differentiates itself in the fact that it need not write zeros across an entire drive. So initialization is done in a matter of seconds. Write a little bit of metadata on a drive and take off from there. And resilvering, we only resilver. It's analogous to a RAID rebuild, for if resilvering is not a familiar term. We only resilver the data that we've actually, the space of a drive that we've actually written data onto. So if we have a 10 terabyte drive in the future here, and we've written 10 gigabytes of data onto it, that drive fails, we put in a new drive, we only need to rebuild 10 gigabytes of data. That's a massive time savings and operational performance savings for the rest of the workload, with ZFS offers that nobody else does. So, get into some of the details of a couple of the bullets there. Data integrity, the superior checksum protection that ZFS has. This gets down to the way data is actually laid out on the drives, on the disk drives, or solid state drives for that matter. On the left-hand side of the screen here, you see the way that we've, in the industry, traditional file systems have been doing data protection on disk for the last 10 to 20 more years. Essentially, the idea is, as you see the blue data box and the green checksum box immediately below it, on the drive, we write data. The industry has written data and a checksum for that data using some calculation, some algorithm, right next to each other. And so the plan is when when the application comes back and says, okay, I need to go read that data back. Let's say that was your bank balance. So your bank balance was $10,000, and the checksum to validate that amount. And then you go back and you need to read that data back sometime future. You go to the teller machine and you want to get your bank balance. So the application goes to the disk and says, okay, I know where that data is supposed to live and the checksum is supposed to be right next to it. Why don't you give me the value of the data block, and then hang on to the checksum for a second. I'm going to recalculate a checksum using the same algorithm. And then now you give me your checksum off of the disk, and I'm going to compare the two and find out if they match. If they match, then I trust the data that you just gave me. If they don't match, then I understand there's a problem. Something happened. The term bit rot is a familiar one in the industry for a bit got flipped, right? Something that used to be a 1 ended up a 0. It could have been a solar flare or somebody passed by with a magnet, or whatever the case may have been. So this methodology that the industry has used, traditional file systems have used for years, has protected against bit rot. The checksum comparison works to determine if the data that's there doesn't match what should have been there from the time we originally wrote a checksum. What it doesn't detect, though, is a whole series of other errors that are very real. Right? If you take any of the listed terms there in the pink, phantom writes, misdirected reads and writes, etc., and go and do a quick search on Google or Bing or your favorite search engine, you'll find some very real stories of very real customers and enterprises that have hit this type of a problem in their storage, and it's caused real issues. And I'll take one as an example: a phantom write. A phantom write is a write where the application told the drive, "Here's a new piece of data." Let's say you used to have a $10,000 bank balance, and you got a nice bonus or won the lottery or something, and you added $10,000 to that. So now your new balance should be $20,000 in your bank, and you've told the drive, "Go right now $20,000 into this space." And the drive comes back and says, okay, I did as you told me to the application. I've written 20,000 there in the new checksum, so when you come back and ask for that next time, it will be there. So now the applicator, the file system keeps track of the location, but not the data in it. That's what the drive is for. That's a phantom write. It said it wrote, but it actually didn't write. So we know that the old balance is still there, the $10,000 with the checksum that matches $10,000, even though it's supposed to be $20,000 and a new checksum to match 20. Unfortunately, the traditional file systems, when they come back in some future time to read the data that's there, all they do is read the $10,000, the value, which is still 10,000 because it was never overwritten, and the checksum that still matches 10,000 because it was never overwritten. They do the calculations and compare and say, sure enough, this data looks to be good, and now your bank balance is incorrect, right? Consider that to be an instruction in the Windows operating system. You get the blue screen. It could be any number of things. But that's a situation where um, a drive essentially lied. It said it did something and it didn't. Traditional file systems have no way of protecting against that. On the right-hand side of the screen, though, ZFS, the way it's laid data out on disk, it does. It can protect against that. And the fundamental difference is that the checksum, that same kind of concept, by the way, our checksums are more sophisticated than most traditional file systems using a 32, 64-bit or whatever checksum. We use a 256-bit checksum, so far more um, cryptographically sound checksum to compare. But in addition, we store it in a different physical location. So if that, as you see on the screen, data, so say that $10,000 bank balance is the bottom left-hand data block, the checksum for that is stored in what we call a parent block, or the pointer block for that, and is stored physically separate, some different place. So now, when we're supposed to update that data block, if we told the disk to go do that, and it said that it wrote the new $20,000 balance where there used to be a $10,000 balance, it would also have to fail to update the checksum and the checksum's checksum and the checksum's checksum's checksum, etc. on the way up, and that becomes realistically impossible. So what we have by separating the checksums physically on disk, we have a means of protecting against all these other varieties of errors that have happened in the past that have not been detectable. Phantom writes, where the disk said it did something it didn't. Misdirected. The drive wrote over top of the wrong place, or read from the wrong place, and then disk drive firmware errors and other things as well. So that's just one piece. We can validate data is the data it's supposed to be by separating checksums from data in the way that we've done this in ZFS. Another thing that's key, and this goes back to the first slide that said always consistent on disk. ZFS is a copy on write file system, and it's important to spend a little time spelling out what that means, copy on write, because it's different than what you might think of when you first hear copy on write as it applies to snapshots, for example, in IBM or NetApp storage. Copy on write for ZFS, as it meant for software development, kind of before that snapshot methodology or terminology came around. Copy on write simply means I can have multiple references to a single entity, a single thing, or a single block of data, for example. But if something changes that block, that thing, that when the change is made, I make a copy of what used to be there and essentially redirect the change to a new place. So there isn't, in our sense, there isn't a copy occurring. It's just if I had an old chunk of data and I'm going to go modify that data, I don't overwrite the old chunk where the old chunk lived. I write it into a new place. I write the modified data into a new place, and if I no longer need the old chunk, then I can forget about that space and I can reuse it sometime in the future. But we never overwrite data in place. That's the key piece to what copy on write means for ZFS. So we'll use a quick example of what's on the trees. You see this kind of layout familiar from the previous screen. You know each of the parent blocks includes some metadata information, including a checksum for the block to which it points. So if you work your way from kind of the bottom left-hand, if you work your way from the bottom of any of these little trees, that's the data, and then you've got metadata, including checksums, working their way up to the very top of the tree, called the Uber block. This is the terminology that ZFS uses. So if we start with number one, the upper left-hand corner there, the initial state of the file system, and we want to modify some data. We want to modify the data, say, on the bottom left-hand side. So we've got two data blocks we're going to modify. The first thing we do, as number 2 shows, upper right-hand corner here, we copy on write, COW, some data. We don't overwrite the orange data that's there already. We write the new versions of that data into new physical places on disk. And then we calculate the checksums for those, and we write the new pointers to those in their parents. Again, the new pointer doesn't modify the existing pointer. It goes into a new place on disk. And then that pointer's pointer gets written to a new place on disk in number 3, right? And then finally, if we get to number 4 and everything has gone well, the last step in updating the file system is we update the Uber block. We update the entry point into the file system. And that happens in the world of ZFS every time we do what's called a transaction group. A bunch of writes may be modifications of data, may be bundled into something called a transaction group. And those are done kind of bottom up. And then if and only if everything has gone well, we update the Uber block as one atomic transaction. That's a terminology from computing, right? Atomic means it either happens or it doesn't. An atomic transaction updates the Uber block, and then now in number 4 we have a new state of the file system, and we've forgotten about the old orange stuff that used to be the old data that used to be there. Now, what happens if we lost power, for example, in the middle of this process? So let's say we finished 1, 2, and 3, steps 1, 2, and 3, but we didn't get to 4. Well, when we come back, when we power the system back on, we never got to a point that a new entry point, a new Uber block that knows anything about the green blocks. So they essentially disappear, right? The green blocks are gone, and the state of the file system is all orange, as in number 1. So it's still perfectly consistent. It was the way it was when we first started to do these updates, and nothing is partially written. So this prevents things like you hear about, or you can go do a little searching on a RAID 5 write hole, where you get through part of your writing, but you haven't updated the parity to match the writing, and now you don't know what's actually true. So you get a potentially corrupted file system. It prevents against things like the requirement for things like a file system check. Right? So if you're familiar with the loss of power in a storage environment, traditionally one of the first things you did when you powered it on is sit around and wait for hours while something goes through and does a check of the entire file system to make sure it's all valid and consistent. So ZFS doesn't have to do any of that. Another interesting note, we talked about snapshots briefly on a previous slide. Another interesting note is if we had taken a snapshot at state number 1, for example, and we wanted now to modify some data, and we go through steps 2, 3, and 4, instead of at step 4 dereferencing or forgetting about the old orange stuff, we would just maintain the pointer into the orange state of the file system like it is in say number 3 there. So now we've got a snapshot. We can easily traverse the tree and find the data at the time of the snapshot. Or if we want the current, we just follow the green Uber block and work our way down through the current state of the file system. So at any point in time, you have a complete and consistent state of the file system, and you can have updates in flight, but if those updates don't complete, that doesn't modify, it doesn't actually change anything on disk, and so you don't have an incomplete write at any point in time. Now, what you might say, what about the data that we started to write and then we lost that data? What happens there? That gets to one of the conversations we'll get to here around the ZFS intent log. So hold that thought for just a moment and come back to it when we get to the intent log. Okay, real quick thought around kind of the layers. So Mark mentioned ZFS is and therefore Nexenta Store is a unified storage platform. The way that this all functions together is there's a bunch of layers here. It's probably worth a deeper conversation another day. We're just covering basics today. But at the very bottom, right, we use block devices. So those are most often hard drives and solid state drives, but they could be LUNs off of an existing SAN device or whatever, anything that provides block storage that we can go and use. We pool that together. We'll talk about the hybrid storage pool in a moment. We handle updates to the file system using transaction groups, as we mentioned. So there's this transactional object layer. And then we can emulate either a volume, a LUN, right, for Fibre Channel, iSCSI, etc., or we can put a layer of POSIX compliance on top of that and talk file protocols like NFS and CIFS. Or we can interact directly with the object layer and do things, interesting things like parallel NFS and interaction with other object-based storage platforms. So Nexenta has done a lot of work in that space as well. So more news to come on that. That's kind of the structure of all that. We get down into how do we actually start using these things and laying them out and build back up to some of the things we were just talking about. In the world of ZFS, we have this terminology called VDEVs, or virtual devices. At the heart of a VDEV is, how about this? Summarize or compare in your mind a VDEV to a RAID set or a RAID stripe in a traditional file system. Under the covers, you have physical or leaf VDEVs. Those are actually not virtual devices, they're real devices. So in the bottom, in the blue there, you have 4 disk drives, for example. 2 of those disk drives have been mirrored, so this is a RAID 1 mirror, for example. We have lumped those together into what we would call a mirrored VDEV in ZFS terminology. And the other 2 drives have been also mirrored. So now we have 2 RAID 1 mirrors in our pool of 4 drives. And there is this root VDEV, which is the pool of storage. So there's a leaf VDEV. The VDEVs in the middle are the ones we usually spend most of our time talking about, and then there is a pool VDEV kind of at the top level. Everything exists within this root VDEV. or pool. So out of 4 drives, in this case, we made 2 RAID 1 mirrors. And then ZFS stripes data across VDEVs. So in the last slide, we had 2 RAID 1 mirrors. In this slide, we have a collection of RAID Z2, or 2-disk parity, dual parity VDEV. So if we have, as you see on the screen, 1, 2, 3, 4, 5, 6, 7 drives in VDEVs, and those are RAID Z2, those would, in your mind, kind of compare them to a 5+2 RAID stripe. RAID Z2 is different than RAID DP from NetApp, for example. The way we do our calculations of parity and things are different and whatnot. But in your mind, you can lose any 2 drives out of that RAID set and still have access to the remainder of your data. So whether the VDEV was a 2-disk mirror or a 5+2 RAID Z2 VDEV doesn't really matter. ZFS then stripes the data it receives across the VDEVs that are available to it. And within a pool, everybody, I mean, ZFS allows you to do others, but otherwise, but you shouldn't. Everybody makes the same types of VDEV. So a pool of 10 drives could be, say, 5 1+1 RAID 1 mirrors, or it could be 2 3+2 RAID Z2 VDEVs, or some combination of single parity, triple parity, etc. So now we get into the hybrid storage pool. And we talked about pieces of this leading into this, and so we're going to dive into the components of it, and then for the following slides we'll get into a little bit more detail around the ZIL and the ARC and L2 ARC. So hybrid storage pool is made up of the disk drives laid out in VDEVs or RAID sets, as we just described. Those are used for, really, they're used for what they're good at. They're used for streaming workloads, and they're used for high density, high capacity, typically lower cost, higher capacity, lower power storage. So more often than not, and we'll kind of get to how this all works, but more often than not, those in the ZFS world, Nexenta world, are 7200 RPM SAS or nearline SAS disk drives of larger capacities, 1 terabyte up to 4 terabytes now in a lot of our new architectures. So, those of you who have been around the industry for a while know 7200 RPM drives inherently don't provide the performance that you might want for your application, which is the reason we've been doing things like faster hard drives, 10K RPM, 15K RPM drives for well over a decade, right? Longer than that. And in order to get performance in the past, without some of the things like ZFS offers, in the past, in order to get the lower latency, therefore higher IOPS, inputs and outputs per second, that you are desiring for your application, you would have to throw more and more disk drives at the problem. So get more and more fast disk drives. You look at benchmarks from companies like IBM and such in not too long ago, and look at the hardware architecture that they put out there to do their low latency, high IOPS systems, and they have massive numbers of 15K RPM drives, 15,000 RPM drives, and they're only writing a tiny little bit of data on each drive, an idea called short stroking. Right? You're actually writing the data on the outside of the disk drive, which means it takes as short a time as possible to get to the data, but you're wasting a whole bunch of capacity on the inner kind of sectors of the drive. So in order to get performance in the past, we've always had to do this short stroking, expensive, high power, lower capacity, fast drives. Where I was just saying a minute ago, ZFS deployments are typically 7200 RPM high capacity drives. So how do we make up the difference? How do we do actually far better than what we used to do with 15K RPM drives in the industry? We use solid state drives. Thank you to Apple and others, Samsung, people who have been driving the popularity of flash technology in the last decade or so, probably a little bit less than that. It's now come to a price point where it makes sense, and you're seeing it become popular rapidly in the enterprise, not just in the consumer space on our cell phones and our thumb drives, but now in the enterprise space as well. So today's flash drives, enterprise flash drives, are far different than the thumb drive you buy at your local office supply store. There are far more advanced wear leveling and other types of algorithms built into these drives. But the price point has come down, where on $1 per performance, $1 per IOPS ratio, they're massively cheaper than hard drives. It would cost you far less to buy one solid-state drive and get X number of IOPS than it would to buy a whole bunch of spinning hard drives to get the same amount of performance. They haven't yet. Solid-state drives still haven't displaced hard drives in the dollar per capacity comparison, though. And therefore, you're seeing this hybrid approach in the industry. people trying to figure out how do we mix the two together, because there's still a strong point that hard drives have, spinning hard drives, but there's definitely a strong point that flash and solid state drives have as well. The projections are that in the future, hard drives will become displaced both on the dollar per performance, as they already are, but also on the dollar per capacity front, as flash gets more and more advanced, and they can squeeze more and more capacity into a smaller amount of space. But we're not there yet, so we need to have this mixed approach. And ZFS has really been leading the industry as we developed it at Sun. I worked in the engineering team at Sun back when this was first becoming available, and now proud to be with Nexensa and continuing the same effort. ZFS has really been leading the way. We've worked with solid state and flash vendors from day one to make this come together. So how do we use flash in ZFS? Number one, let's do talk about the writes, and the opposite of left, or the opposite of reads. So the writes. We use solid state drives in the ZFS intent log, and more aptly named a separate log device. ZFS intent log, we'll talk a little bit more about this in a minute, to accelerate writes, and specifically a certain type of writes, what's called synchronous writes. So if you're familiar with NFS, for example, use that protocol. NFS, the protocol, defines certain writes, certain operations, like the creation of a directory, the deletion of a file, certain types of writes, but not every write. Those operations, NFS protocol defines them to be a synchronous operation or synchronous function. Other writes or other things can be done in an asynchronous fashion. What synchronous means in that scenario is when the application does a synchronous write to the storage device, whatever device it is, Nexensa, NetApp, IBM, Hitachi, pick your vendor, that storage device is required, for synchronous writes, is required to put that data into a non-volatile, stable storage location before it can acknowledge that write back to the application. So the application thread that did that write is essentially sitting there and waiting for some period of time for the storage to receive the data, write it into a non-volatile place, and send an acknowledgement back to the application. Says, I got it, and you don't have to worry about it. It's in a stable place. That's a synchronous write. An asynchronous write is kind of the opposite in that the protocol doesn't require the storage device to put it in a non-volatile location. So you can put it somewhere volatile, somewhere that if you lost power, you lose that data. But that's an inherent understanding within the protocol. So people who are writing, the developers of the applications, may use asynchronous writes of data and do local buffering or something to protect against that data. Or it may be data they don't care about, right? We're making a best effort to store this data, but it's not a big deal if it gets lost. So it depends on the application, but there is a place for both asynchronous and synchronous writes. But synchronous writes are really the ones that dictate the performance of an application, because, again, that application thread was stopped and waiting for some period of time while the synchronous write took place. So the faster you can complete that write and acknowledge it back, right, the lower that latency is, the time to accomplish that operation, the faster the application goes, because every time it stops and waits, it waits for a shorter period of time and it can carry on. And multi-threaded applications as we have today, of course, are doing lots of writes at the same time, but if we improve every individual write speed or lower the latency of every individual write, the application performance is going to go up markedly. So how have we done this in the industry in the past, right? Again, years and years ago, not that long ago when you think about it, years ago, we had to write to a bunch of different hard drives and wait milliseconds for a write to go out to a hard drive, because that was the only non-volatile place we had. As we move forward in the industry, in time, we've introduced things like non-volatile RAM. Right? RAM inherently is much, much faster to write to. It can happen in nanoseconds or picoseconds even. We can write data into, probably nanoseconds, we can write data into RAM. But the problem with RAM is it's inherently volatile. It takes power to hold that data there. If you lose power, that's gone. Same reason that we've learned for years and years to save our work as we go on our laptops and our desktops, because if we lose power and the system goes down, all the work that you had that was stored in that volatile RAM place, that data is gone, unless you wrote it off to the non-volatile spinning hard drive. So in the case of what we're doing here in the industry, right, NVRAM, non-volatile RAM, we've used folks like NetApp, right? NetApp will still sell an NVRAM card. It uses a battery to provide the extra power to hold that, keep that data in RAM, which is fast to write to. So now you're accomplishing what the protocol requires. You're writing to a non-volatile space because it's RAM, which is fast, but it's got a battery to back it up. As we look across the industry over the years, right, batteries have problems. Batteries wear out. You know that from your vehicle. You know that from your flashlight. You know that from your kids' video games. Batteries wear out eventually. In order to make them last longer, you have to do fancy things like fully charging them and letting them discharge, at which point your data is at risk for a short period of time. So you have to lose some of the benefit of your cache speed and all kinds of things. There's a lot of things that we've done in the industry to make batteries work as well as we can. But again, coming back to Flash, Flash has come into the market in a place now that can displace and do a better job of what we've been trying to do with NVRAM for years, the last several years. So again, ZFS uses Flash, and we use it as a much faster, lower latency write destination for synchronous writes. So instead of writing to a spinning hard drive, we write to non-volatile Flash. It typically would be SLC. If you get into the Flash world, you talk about single level cell versus multi-level cell. It's typically single level cell, faster to write to, versus multi-level cell. It doesn't wear out as fast as either. For that heavy write load of the ZFS intent log placed on a separate log device or a slog. There are vendors in the industry. We work with a variety of them. STEC or STEC is one that stands out in a form factor of a drive they have that actually in your mind uses RAM, Flash as a non-volatile destination, and a supercapacitor, which doesn't have all the downsides of a battery, but provides that same concept of backup for your power for the RAM, volatile RAM destination, then they can flush that out to non-volatile Flash if needed. So that all happens within a single disk drive form factor. But we work with a variety of vendors in the Flash space to do interesting things. So we use Flash to do synchronous writes quickly. Asynchronous writes can go right into the system RAM and don't have to worry from there. So that's the write side, the kind of the more complicated side. The read side of the hybrid storage pool takes advantage of RAM in the controller. Controller in your mind, think most of our deployments are a server connected to some disk shelves. So if you're familiar with Dell, for example, right, we're hardware agnostic, so we work with Dell, HP, Supermicro, IBM, Cisco. Pick your vendor. We've got a hybrid hardware compatibility list. But if you're familiar with Dell as an example, an R720 server connected to an MD1220 JBOD, for example, might be a configuration. We've got some of those certainly out in the field. And connected with an HBA and a SAS cable between the two. So the RAM in that the R720 server we use as cache space. So again, compared to NetApp, and not to disparage them at all, certainly they've led the industry for a long time, and I've got good colleagues there. They have controllers that may have 32, 64 gigabytes or so of cache space for reads. So if the data that you need is in cache, you can retrieve it. The application gets it very, very fast. Again, low latency is what we're driving for. But it's a limited cache space because we use servers. Nexenta is software only, and we sell, it runs on commodity hardware. Because we use servers, you can fill up the server with as much RAM as it can contain. An R720, I think, can go up into the 700, 800 gigabytes of RAM, for example, with current DIMM sizes. So that means you could cache 3/4 of a terabyte of data in RAM and have very high performance across a pretty large working set there in RAM. But if that's not enough, let's say, for example, you didn't have that much RAM. Let's say you put 128 gigabytes of RAM and you had a 30 terabyte database, and you've got 500 gigabytes of that is kind of hot data that you're actively working on. We'll come back to this a little bit more later. If that 500 gigabytes is hot data, we'd really like to have all of that in cache. So you get low latency, fast reads out of that data back to your application when it requests it. You don't have to wait for spinning hard drives. Even the 15K RPM drives are going to still take milliseconds to retrieve that data. Maybe faster than multiple milliseconds with the 7200 RPM drives, but Flash is going to retrieve data in microseconds, so order of magnitude faster. So if you need a 500 gigabyte cache space and you only have 120 gigabytes of RAM, no problem. You put a couple of read optimized, typically MLC cache solid state drives into your system. A couple of 200 gig devices, for example, and now you have another 400 gigabytes of cache space that we call the level 2 adaptive replacement cache. And now you have over 500 gigabytes of cache available, and you can have very high performance applications with large cacheable amounts of data and still not have to rely on the spinning hard drives for all of your performance. So all that to say, automatic and intelligent use of RAM, solid state drives in two ways: for accelerating synchronous writes and for expanding cache for the read side. And then, as I said at the outset of the slide, we really relegate the spinning hard drives to what they do best, which is provide the capacity storage we need behind the flash that delivers the performance. All right, so we'll dive into each of these just a little bit more. I touched on a lot of it looking at this slide because it really fits together in this picture well. The ZFS intent log, as I mentioned, used to satisfy synchronous writes. A couple of examples there. All block writes, for example, for iSCSI, Fiber Channel, and other block protocols coming. It's an option, but strongly recommended to treat all writes as synchronous. Therefore, a ZIL, or a write accelerator solid state drive, is key to any architecture that's going to be a block-based architecture with Nexenta. The idea here is, iSCSI, Fiber Channel, for example, those are all based on the SCSI protocol. And think back to when you use SCSI to talk to a single disk drive. The assumption is when I make a write to the disk drive, it's there. There's not really a concept of an asynchronous write in those protocols. So you put potential data at risk, if you will, if you treat it asynchronously and let the storage acknowledge it from RAM. You really want to treat all writes for Fiber Channel and iSCSI as synchronous, and then therefore take advantage of the benefit of a ZIL or slog device out there to accelerate those. And as we discussed, not used for asynchronous writes. Just a terminology clarification, the ZFS intent log, the ZIL, exists in any pool, any hybrid storage pool. It will exist on spinning hard drives if that's all you have, but the slog, the separate log device, is where we can take that intent log and place it specifically on the solid state drive that we designate to be that low latency cache device. There's a couple scenarios where you might not want to use a slog, and that would be in high throughput synchronous applications. So if all of the writes you're doing are synchronous, but you're doing a massive amount of them, very, very high throughput, you're flooding get multiple gigabytes a second to the server, that may be faster, that may be more throughput than the solid state drive can actually handle. Right? Many of the solid state drives we see are out there rated at 500 or so megabytes a second. So you'd either need several of those to share that load, or really ZFS can bundle all of those writes and just flush them out to the spinning hard drives at a good clip, and therefore you get the benefit of a bunch of spinning hard drives sharing that load, which they do very, very well. So in that scenario, you can set the log bias, a setting in Nexenta Store, to latency to use the slogs, or throughput to bypass it. And then there's a command there that you can jump into the command line interface with Nexenta Store and see the performance that your ZIL, the ZFS intent log, is giving you. All right, coming back to caches again, I spoke to most of this, so we'll move through these slides fairly quickly, and we're actually getting pretty close to the end. Traditional caches work well when data is being accessed the data that is being requested was recently accessed. Most traditional caches are based on a most recently used MRU type of algorithm, which means if I have 100 gigabytes of cache space, or let's say NetApp controller, I have 32 gigabytes of cache space, and I read a gigabyte of data, that goes kind of in the top of the list. And then if I continue to read more data, but not that same piece again, it moves down the list until eventually it gets kicked out, and because I've read another 32 gigabytes of data since then. But it really doesn't work as well when you've got data that you're trying to access frequently, but it may not be the most recent thing you access. So there's really kind of been this cache problem that we've had with frequently accessed data that gets evicted or kicked out of the cache because we don't have enough space there. So how do you solve that? Either you get a bigger cache, which you can do with ZFS, or you add a more sophisticated algorithm to manage a balance between recency and frequency. And that's really what ZFS has done in its adaptive replacement cache, or adjustable replacement cache you'll hear sometimes as well. So really we have kind of a two-part buffer in our cache. One is based on the most recently used data, and one is based on the most frequently used data. And I won't go into the details here. You can certainly do some reading on it. But ZFS automatically manages those two. And they're not fixed space. It's not divided in half. It adjusts automatically, kind of intelligently along the way. And then data that hasn't been either frequently or recently used can be evicted or dumped out. Again, this amount of cache space can be massively larger than most of your traditional hardware. storage hardware as well. So again, we talked about this a little bit before. The layer 2 ARC is really just an extension of that same idea. So data that is about to be kicked out, let's say we have 128 gigabytes of RAM, and we're filling that up, and we're accessing data more frequently than we access some old data. Eventually, data will get squeezed out, but as it gets closer to that, ZFS goes along and says, all right, this data is probably going to get evicted soon unless we access it again here pretty quickly. So intelligently behind the scenes, it can go pull that data or copy that data out of the ARC and put a copy of it into the layer 2 ARC onto those solid state drives. The directory for that, kind of the index for that, lives in memory, so it's real fast, to figure out where to go look. And we can then, if data is requested and it doesn't live in the ARC, but it does live in the L2 ARC and the solid state drives, we can pull it from there in microseconds, again, much faster than a spinning hard drive. So the kind of the order of speeds or latency is picoseconds to nanoseconds to access data in the RAM in ARC, microseconds to access data in L2 ARC and solid state drives, and then milliseconds to access data, even if you've got the fastest hard drives out there from the spinning hard drives. So works well when you need that low latency, larger working set than what you can fit into a memory. And because Flash is still kind of fits in that dollar per performance space between RAM and between his disk drives, it's less expensive than buying a whole bunch of RAM, but it's more expensive than buying a bunch of capacity in buying all your capacity in solid state drives. It fits nicely in the balance in between there. That said, we have lots of customers that are running all solid state drive pools because they need just the ultimate performance they can get. So that works as well. But that's what the L2 ARC is about. And again, you can monitor the usage of that with a show performance ARC command in the command line interface. One concept I've alluded to a couple times here, I want to make sure that we kind of drill on as the last concept before we wrap up, is this idea of a working set size. So this is specific to the read side of the equation, so that balance between the ARC, L2 ARC, and spinning hard drives. There's a couple different ways you can define this, but the average working set size, or WSS, as you see in some of the Nexenta documentation, is the amount of space needed to satisfy immediate storage needs of an application. So it's immediate is time bound. It's some amount of time. So you might say an hour. Let's say it's the amount of data that I'm going to be actively working on in a given hour. Another way to summarize it is the frequently used space or subset of my data. So we used the analogy of a working set, or we used the analogy earlier in a working set size without calling it that, when we said we have a 30 terabyte database, and 500 gigabytes of that is kind of the hot data. Is really the working set. It's what maybe that's the last quarter's data or the last month's data. Right? Amazon might have a massive database, but during the Christmas season they have a lot of actively happening orders, and there's going to be a subset of those large databases that are the working set or the active workload in a given period of time. So what we want to do to get the best performance possible is to fit that working set into low latency media, into RAM plus solid state drives. If part of that working set is still being pulled off of spinning hard drives every time it's accessed, and it's being accessed a lot, then we're relying on spinning hard drives again for performance. So this is the sizing balance that my team really, again, I lead the sales engineering team at Nexenta. The sales engineers at Nexenta and our reseller partners, technical staff as well, are here to enable and help customers work through what's the right balance of all these different pieces. Nexenta is infinitely flexible with the hardware that you can buy and put it on and the ways it can be configured, but there's some guidance we can provide around this. So one of the ways, a couple of thoughts around this, right? You can either buy certainly enough RAM and solid state drive to fit your working set in there, or you can reduce the size of your working set, or a combination of the two, certainly. One of the ways to reduce working set size is to use snapshots and clones. So if you have a virtual machine, for example, and you take a snapshot of the virtual machine to make a second one, and that's a clone now, just to differentiate. Snapshot is a read-only, clone is a writable snapshot. We only have one instance of all of that data in memory or in the L2 ARC if needed. And only when the second virtual machine then writes data that's different from the first one does it start taking up new space. So we get to share some of RAM, or we get to share some of the L2 ARC between multiple virtual machines in that scenario, but there could be many other scenarios. and therefore we're efficiently using that space. Compression works as well, right? We can compress data and therefore use um, less space in RAM if we're working on compressed data. Deduplication similarly. So there are ways to reduce the working set size, and then of course architecting your hardware to match it is the goal. This should be pretty familiar, these concepts. So a couple of just graphics to go with it. There's this idea of kind of a performance envelope or a difference in performance. Clearly, RAM, the ARC is going to be lots more IOPS because it's very, very low latency, as we said, kind of picoseconds, nanoseconds per I/O. The L2 ARC is going to be slower, certainly, than RAM, but still massively faster than spinning hard drives by an order of magnitude. It's going to be in the order of microsecond latencies. And then the spinning hard drives, again, doesn't matter if you do 7,200 RPM or 15K RPM, they're going to be there for what's left. So we want to fit the ARC and L2 ARC, the working set, if possible, into the ARC and the L2 ARC as much as possible so that we get the benefit of the low latency, high performance media for the working set we care about. And then the cold data, the data that we're not accessing regularly, lives out there on the spinning hard drives where they do what they do best. So one last piece to consider in all this, right? We talk to customers and often they get excited about this. Wow, I can get these massively performant systems. I'll just scale out my RAM and my L2 ARC to be huge, and we'll fit just tons of data in there and really low latency. I can do 10 bazillion IOPS. Couple things to think about. Don't forget that the bottleneck to your performance exists somewhere. There is always a bottleneck to the performance of your system. It may be within the storage hardware that you purchased. It may be outside of that. It could be the application hardware or software may not be able to ingest or spew out data as fast as you would want it to. There may be a network pipe or network bandwidth limit between things. Any number of places. It certainly could be in the configuration that we just described here. But for example, take a look at the graph on the screen. We've got 3 different scenarios here, right? 3 different kind of combinations between RAM, L2 ARC, and then some spinning hard drives. And you see the performance envelope that we just talked about on the last couple of slides traced out there. But there's one more line added there, and that's that red line. And that red line is the maximum amount of data that you can force through a 10 gigabit data connection if you're doing 4K IOs. So at 4 kilobytes of IO, you can do upwards of 300,000, almost 300,000 or so IOs per second, and you will have completely utilized the slightly over a gigabyte per second of bandwidth that you have in that 10 gigabit link. So it doesn't matter if you filled out your RAM and you've got the capability of doing all these other things. You're going to have multiple 10 gigabit links to even sustain that amount of bandwidth. So again, just driving home this concept that we have to look at, and again, this is what my team does every day with our customers. We have to look at the complete architecture and consider from the client application all the way through to the storage and back and everything in the middle, what is required, and what is there, and what performance do we want to get, and what do we need to do to architect toward that. So I think that really covers the majority of what we wanted to get to. Really, the key topics for today were the basics of ZFS, the features it brings to the table, the hybrid storage pool, and what the individual parts of that are all about. The last thing I want to leave you with, if this is just kind of sampled or touched on some of the detail you'd like and you want to go deeper, there's a bunch more out there to read. The first link there, the ZFS education link to Nexenta, covers a lot of what I just discussed and some of it in more detail. Some folks on my team and others have written a handful of white papers in that space. There's a few links from a former colleague of mine, a good friend of mine, Brendan Gregg, works at another Illumos-based company called Joyent now. He and I worked together at Sun Microsystems back when ZFS was being developed, and he's written some good detailed blog posts around the inside inner workings of the ARC, L2 ARC, and the slog or the ZFS intent log. So if you want to go and do some more reading and get some more detail, feel free to follow up with any of these links or contact us. Again, we're here for you, whether you're a reseller, partner, prospective, or current customer, or anybody. We are here to help you. My team is available. Contact me at chris@nexenta.com. Contact sales@nexenta.com to reach the entire sales team, including my sales engineering team. And we would be happy to help you architect your enterprise class storage or work with you for your Nexenta customer as well. So with that, I thank you for your time. I hope this was useful, and any questions or comments or feedback, please reach out to us, and we'd be happy to hear from you. Have a good one.